So we're going to cover that. What is turndown ratio? What does it mean to us? What determines the turndown ratio for a device? How do we calculate the turndown ratio? We're also going to talk about theory versus reality. You'll see that that may be pretty different for most of the pumps. And we'll also show you what we advertise as our turndown ratios for our pumps. Again, you'll know by then that is the theoretical turndown, and you'll be able to pick to see if that is practical for the application that you're working with the customer for or not. So hopefully this will answer a lot of your questions. Before we get started, we just want to cover the term ratio. What is a ratio? We're just comparing one thing to another. Okay. So in this example here, you see we have 3 blue blocks and we have 1 yellow block. So the ratio is 3 to 1. You can see you can write that a few different ways. It's all synonymous. It all means the same to us. 3:1, it's 3 to 1. 3:2, use the word 2. 3/1, just as a fraction. All meaning the same thing. It all relates to comparing one thing to another. You may see it where people haven't brought it down to its lowest denomination, where instead of 3 to 1, you might see it as 6 to 2. So obviously, if you divided the 6 by 2 and the 2 by 2, you would get down to 3 to 1 again. It's still the same meaning. It's still really the same ratio, but it's just expressed a little bit differently. Okay. So what is turndown ratio? It's defined as the rated capacity of the pump divided by the minimum capacity of the pump. The rated capacity, the rating that we give with our pump, of course, is with water, and it's its maximum. So if you turn both the stroke length and the speed of the pump up to its maximum, that's what we rate our pump. That's the rated capacity of the pump. Now we're saying divided by, or 2, compared to the minimum capacity. So that is still while maintaining the reliability, the accuracy, the linearity, the repeatability of the pump. All the things that we advertise the pump is capable of doing, we're saying this is the minimum that we can turn it down to and still count on those numbers to be accurate. So obviously, the higher that first number is, the better the turndown. We can essentially use that number and divide our rated capacity by that, and that's going to be our minimum capacity that we're saying we can turn it down to. So you'll see, as I mentioned, the higher that first number, so 20 to 1 is better than 10 to 1. Most likely when you see someone with a requirement or a turndown ratio, a requirement for that, most often it's 10 to 1, which is relatively low. We should be able to use 10 to 1 on pretty much all of our pumps at very minimum. What does that mean to us? Again, it gives us an idea of what the low end of the pump will be, or the very lowest that we say we can do, still maintain all of those parameters, the reliability, the repeatability, the accuracy. So it helps us determine which of our pumps best fits the customer's application, which best fits their flow needs. Specifications, particularly on the municipal side, they tend to insist on sizing a pump based off of growth in a community. So they'll build a water plant and they want to put a metering pump in to dose whatever chemicals they're putting into the water to treat it. And they'll base it off of growth in that community. They may say that in 10 years, the population is going to expand 4 times. So they're going to have 4 times as many people. And in theory, you would think that they're going to use 4 times as much water 10 years from now than they are today. So in that case, that means they're going to have to dose 4 times as much chemical in 10 years than they do today to treat that 4 times the amount of water. So they'll size that pump when they're building that water treatment facility to anticipate growth in a community. So that's why they'll specify a turn down to size the pump in. Now, what determines the turn down ratio? Well, if we look at how the pump operates, we're moving that diaphragm back and forth. Of course, we pull it towards the drive. You'll see the picture to the far left. We're pulling that diaphragm to the left. The next slide, you see we create a cavity there. That negative pressure pulls the valve balls towards the center. The bottom lifts off of its check seat. The top one is pulled down into check. And that negative pressure is going to lift the fluid into that cavity that we created. Then we energize that diaphragm, either energizing the solenoid or the cam follower comes around or is pushed by the cam, and we displace that fluid, that volume that we pulled in, and it pushes the valve balls away from the center, pushes the suction at the bottom down into its seat. It's in check. Flow cannot go in that direction, so the pressure forces the valve ball at the top open, and we push the fluid out towards our process to complete that stroke. Now on that, we have 2 different adjustments. We can limit how far we're pulling that diaphragm back, and usually most of the pumps are using a spring to pull the diaphragm back. So we can limit how far that's going to pull the diaphragm back, which in essence limits the size of that cavity. So that limits the volume that we pull into the liquid end, and then how much we can displace on the discharge part of the stroke. So we have a limit of stroke length, and we can also control how often that happens. Usually we talk about frequency, and we describe that in strokes per minute most often. So we have those 2 adjustments, and that controls flow. So now to determine the turn down ratio out of those 2 adjustments, you use a product of what you can turn down each of those adjustments. So how far can we turn down the stroke length, and how far can we turn down the frequency? So in theory, for example, the gamma L pump, the stroke length will say that we can turn it down to 10%. So the maximum stroke length, again, maximum to the minimum, comparing as a ratio, we say we have 100% stroke length, and we'll divide it by 10%. So that gives us a turn down of 10 to 1. So we've got a turn down on our stroke length of 10 to 1. On the frequency, the gamma L pump will allow us to turn the frequency down to 1 stroke per minute. So the maximum across the board on all gamma L pumps is 180 strokes per minute. So the maximum divided by the minimum, we have a turn down of 180 to 1. So now we have the stroke length 10 to 1. We have the frequency of 180 to 1. If we multiply those together, our turn down on the pump, the entire pump, is 1,800 to 1. 180 times 10. So from the previous slide, we would need to set the stroke length at 10% and the strokes per minute to 1. Now, We can do that. We can physically do it. It will allow us to do it. If the hydraulic conditions of the application are correct, the pump will function. It will be repeatable. It will be accurate. But is that practical? Is that really practical for the customer's application? Let's use the example of a process where we have 1,000 gallons per minute flowing in a pipe. Let's say our dosage needed, our ratio of that dosage, so we have 1,000 gallons, we need 1 ounce of chemical per 1,000 gallons to treat it, to disinfect it. We could have a pump that delivers that 1 ounce of chemical into the 1,000 gallons in one stroke of the pump. One stroke, 1 minute time, an entire minute of flow goes past. Now the pump doses again. It doses that 1 ounce of chemical in. We've met that ratio that we needed to provide. We've done our job. We are right where we need to be. But if we took and turned the stroke length down to 10%, turned the frequency up a little bit more often, so now we have 1/10 of an ounce going in. We would need it to go in every 6 seconds, right? Now that product, that disinfectant, is going in more often, and it will be more efficient for the process. So the chemicals, it's getting mixed in better. A smaller amount more often. Okay. Now, depending on what that disinfectant is, there might be a limit on how far we can turn it down. Okay. We usually say that 30% is the minimum that you should turn down the pump. So more realistically, you would divide the maximum, again, is 100% stroke length, divided by 30%. That gives us a turn down on the stroke length of 3.33 to 1. And if you actually look at a Gamma L pump at about 30% on the stroke length, not about, but at 30% on the stroke length, there's actually a little bar that highlights that range below 30%. So our recommendation is usually 30% is a minimum on the stroke length. So that would be a very realistic or practical turn down. In fact, if we're dosing a chemical that off gases, like sodium hypochlorite, our recommendation is usually 50% minimum on the stroke length. Now, we know for sure there are applications out there that run well below both of those numbers, 30% or 50% for auto degassing or chemicals that off gas, I should say. And that's fine. If it works in your process, that's great. You know, it's kind of a rule of thumb. 50% stroke length is saying that we should have enough volume per stroke that percentage of gas coming into that overall volume is not going to affect the flow of the pump. It's a good practice. But remember, we have other ways of dealing with that vapor that might enter as well. So now for the frequency, we're going to say that, well, maybe 10 strokes per minute might be the max, the minimum that we should dose that chemical into the process. So again, the Gamma L pump will do 180 strokes per minute maximum. We're going to say that 10 strokes per minute, so now we have 18 to 1 on our frequency. So at 30% stroke length, our turn down is 3.33 on the stroke length. And at 10 strokes per minute, the frequency turn down is 18 to 1. So again, we multiply those together, 3.33 times 18. Our overall turn down for that pump that is much more realistic is 60 to 1. That's still well above where most of the requests come in at. Usually a request is asking for 10 to 1 turn down. So what do we advertise? We advertise the same way all of the competition advertises. And it's based off of theoretical numbers, the maximum that you could do if all of the hydraulic scenarios are in your favor or the way the pump needs to see it. The Concept Plus pump, only 40 to 1. Remember, we only have 4 selections for the speed, for the frequency. It's in 25% increments. The Beta pump is a little bit better. We have 10% increments on the Beta pump. The Gamma L, you can turn it down 1 stroke per minute at a time. 180 is the maximum. We'll come back to the Delta pump. We'll talk about that. The Xtronic pump has stroke length as well as a frequency adjustment on kind of a manual mode of operation. And, be careful on the Xtronic pump. Depending on how you want to control that frequency, you have to order it that way specifically. Now we move over to the column on the right, and we see that the Sigma Basic is only advertised as 10 to 1 turn down. The Sigma 1 Basic, we only give the controls, the only control that we have is the stroke length adjustment. Now, quite often people put a DC motor on there with an SCR drive or an inverter duty motor with a VFD to adjust the speed that motor is running at, which changes the frequency that the pump is pumping at. Well, those limitations are based off of those 2 products. You need to know the turn down on the motor, the turn down capabilities on the motor. You need to know the turn down capabilities on the VFDs as well. 2 very common VFDs that we use here, relatively inexpensive, are the Lens, the AC Tech, as well as the Allen Bradley. And both of those have 60 to 1 turn downs. So you can turn it down to 1 hertz, which is very low. That's a very low speed to run the motor at. Depending on the motor, you may not be able to run it that slow. So you have to look at both of those products, both the VFD or the SCR drive for a DC motor, as well as the motor itself, whether it's the DC or the inverter duty motor. Whichever one is the lowest turn down, that's the one that you have to use on your calculation for the overall turn down. The Sigma control version, depending on which gear ratio pump we're dealing with, has up to 2,000 to 1 turn down. So it's a very high turn down capability. The Sigma 2 has an HK liquid end to offer. That's the packed plunger liquid end. We have a turn down of up to 100 to 1. That stroke length control on the HK is a little bit more finite. It has a little bit longer stroke length, so we have a little bit better control over that stroke length as well. The Macro, the TZMB series with a variable speed motor, we can have maybe 100 to 1. Again, all of these are at 10 to 1 or better. See that? Going back to the Delta pump, you'll see it's at 36,000 to 1. That's a very high turn down. That's astronomical turn down. We can achieve that because, remember, the Delta pump will allow you to turn down the frequency to 1 stroke per hour. Not 1 stroke per minute, but 1 stroke per hour. So 36,000 to 1, that means we have 1 stroke, an hour's worth of process goes by, and then we have another stroke. That is theoretical. Can we do it? Yes. Can we be accurate? Yes. However, is that practical? Is that realistic for a customer's application? Most likely, that's not good for the customer. However, one thing that the Delta can do, we can also control the speed at which the diaphragm moves. The Delta, the maximum stroke length at 100% is 2 millimeters. we can have it take up to 3 minutes to move the diaphragm on the discharge stroke, 3 minutes to move that 2 millimeters, or any percentage of that 2 millimeters. So now, where in other scenarios we have one dose and 60 minutes worth of water goes by before we have another dose, we would have one dose and 57 minutes worth of water would go by, or process would go by until we have another stroke. So it's a little bit better, but that's still a very long time without any chemical going into the process. Most likely, that's not realistic for us. If we can have a little bit higher frequency, we can have almost a continuous flow out of that delta pump. So you can look at that. It still has very high turn down capabilities, but we still have to see what is right, what is best for the customer's application. So hopefully that answered a lot of questions that you might have had on turn down ratios. I'll do my best to answer any kind of question you might have. I would ask that you use the go-to webinar toolbar and type in any kind of question that you might have into that section there. Try to address those. Okay. Well, I will mention while you're thinking of any questions to type in, I will mention that we try to have these webinars every week. We try to have them every week at 8 a.m. and 11 a.m. Eastern Time. So we welcome you to join us, whichever time is most convenient for you. If you ever miss one of them, we record them and we post them to our website. That's prominent.us. The easiest way to find them is at the top, there's a search field. Just type the word video there, and we'll bring up the entire list of all of the webinars that we've done, that we've recorded, and you can watch those at your leisure. Maybe this weekend when you have some friends over, and invite them to watch a couple of our webinar presentations. Okay. Here we are. Why is minimum strokes per minute limited to 30% of maximum? It's not the stroke speed, the frequency, strokes per minute, that's limited to 30%. It is the stroke length. That's what we're suggesting to be the minimum. It's not physically limited. You can actually turn it down further. We know that there are applications that run below that 30% recommendation, for sure. 30% is what they're saying will activate those valve balls properly on the stroke length. So you need a certain volume per stroke to efficiently be able to actuate the suction and discharge valve balls. So it's just a recommendation. Again, we know that there are applications out there that run well below that. We're saying 30% is probably where we should size it for. If you can run below that, it would be something that you have to test out in the field in your actual process.